Let me start you off with a quick puzzle. One database, and the cable between two data centers suddenly snaps. Some systems throw you an error right away. They'd rather not serve you at all for a moment. Others keep answering, but what they show you might be data from 3 seconds ago. Which one do you think is doing it right? The answer is both. Depends on what you're selling. If you're a bank, showing me the wrong balance is worse than just erroring out. If you're a social app, nobody cares if the count lags 3 seconds. But if the feed won't load, I'm uninstalling on the spot. Same network failure, 2 completely opposite right answers. And behind all of this is today's star, the CAP theorem. And as always, we're not just talking theory today. I spun up a 3-node database on my own machine, cut the network between them by hand, ran the same reads and writes twice, and let you watch the 2 designs go their separate ways. Every number you'll see came out of a live run. Let's put 3 words on the table: consistency, availability, partition tolerance. What CAP says is this: in a distributed system, you can have at most 2 of these 3 at once. Consistency means every read gets the most recent write, or it hands you an error. It never fobs you off with stale data. Availability means every request gets a response, but no promise it's the latest. Partition tolerance means when the network splits into pieces, the system keeps running. Here's the most crucial point, and the one the most people get wrong. Partition tolerance isn't an option, it's a given. The moment your data spans machines, the network is going to break. Not if, but when. So P, you have no choice but to take. The real choice only happens the instant the cable snaps. At that instant, you keep consistency or you keep availability. Pick one. Flip it around. When the network's healthy, you get both consistency and availability, no trade-off. So don't treat CAP as, quote, I'm always picking 2 out of 3. It's the instant a partition hits, pick one of C and A. We'll step on this misreading again later. Follow your gut, and you might say, I'll just synchronously replicate to every machine, and a write only counts once all of them are done. Isn't that both strongly consistent and highly available? Sounds lovely. The cable snaps, and that dream shatters on the spot. You want to write, and synchronous replication has to wait for the machine on the other side to confirm. But the other side is now out of reach. So you've got only 2 paths. Either you hang there waiting indefinitely, that's unavailable. Or you give up waiting and write locally, and now the other side is out of sync with you. A partition hits, and having it all gets knocked flat. You still have to choose between consistency and availability. Talk is cheap. Let's play this choice out on real machines. 3 nodes, A, B, C, holding the same copy of data. In a moment, I'll manufacture a partition by hand. Wall A off on its own, and keep B and C together as a group. That's simulating the cable that snapped. First design, keep consistency. The technical name is quorum. The rule is simple. 3 machines, read or write, you need 2 of them to nod before it counts. Why 2? Because a write needs 2 and a read needs 2. Write 2 plus read 2 is greater than 3, which guarantees at least one of the 2 you read from just got the newest write. The math has your back. What you read is always the latest. Now the cable's cut, and A is isolated. A client hits A and tries to write 1 record. What happens?
A side just refuses service. It can only reach itself. 1 machine can't make 2, so the write is ruled unavailable. At the same moment, a client hitting B's group, the write succeeds. B and C, 2 machines, exactly a majority. Reads work the same way. Read through A, unavailable. Read through B, you get the value that was just written. Through the whole thing, not a single read is wrong. Either it gives you the latest, or it honestly errors out.
Look at the choice it made. It would rather take the walled-off A side completely offline than show you data that might be out of date. In CAP's terms, it chose consistency and gave up availability. The minority side sacrificed. Same workload. Now let's switch to the second design. Keep availability. The rule flips. Whoever you write to counts, no waiting for a quorum. Write to whatever you can reach and sync it up slowly later. Same partition as before, A is isolated.
This time, both sides stay alive. A client writes a value to A, succeeds. Another client writes a different value to B, also succeeds. Here's the problem. Read through A now, and you get the first value. Read through B, and you get the second value. The same piece of data has diverged into two versions, and both sides are serving normally. When the network heals, the two groups reconcile, and by prior agreement, the write with the later timestamp wins, so all three converge to one value.
This is the price of keeping availability. Neither side goes offline, but in that middle stretch, you might read stale, even self-contradictory data, and you have to wait for it to become eventually consistent. While we're here, let's nail down the 3 levels of consistency. The strongest is strong consistency. Write it, and you can read it immediately, exactly like that CP read a moment ago. The middle one is eventual consistency. Everyone lines up after a little while, the AP kind. The loosest is weak consistency, best effort, and you might not read it at all. Sounds terrible, but a live video call dropping a few frames is exactly weak consistency chosen on purpose, because it can't afford to wait. There's no best consistency, only the most fitting one. Watching normal reads and writes isn't enough. The real test is how it dies. Let's look at one of the most common failure paths. Primary replica failover. 1 primary, 2 replicas, asynchronous replication. A client writes 10 records back to back, and the primary on each one immediately says, saved. But the replicas are catching up behind, with lag in between. Now, at exactly this juncture, the primary crashes.
The moment it crashes is when the books are clearest. The client was told records 1 through 10 all committed successfully. But in reality, the first replica only copied through record 8, and the second only through record 7. Failover has to pick the most up-to-date replica to take over, and the best one only reaches record 8. So what about records 9 and 10? The client thought they were safely stored. Actually, they went down together with the old primary. Gone. 2 already acknowledged writes vanished into thin air.
This is what that textbook line, failover carries a risk of data loss, actually looks like. That data loss window is exactly equal to the replication lag. However far ahead the primary runs of the replicas, that's how much you can lose. So what if we switch to synchronous replication? Every write waits for at least 1 replica to confirm before it replies to the client. Now, if the primary crashes, 0 loss. But the price is, every single write pays 1 replica round trip of latency, and it slows down. See the trick yet? This is the same knob as the cap thing from a minute ago. Turn it toward consistency and durability, and you have to give up latency and availability. Turn it back, and it reverses. Different failure scenario, same question. So in the AI era, how does this piece shift? Same drill as always. 4 questions, no hype, no bashing. 1. What does it help with? The cap trade-off itself. AI can't help with the core of it. Because can this data be stale? And for how long is a business semantics question. Someone who understands the business has to make the call. What AI can help with is the stuff around the edges. Placing replicas based on traffic forecasts, watching for replication lag to suddenly spike and firing an alert, scoring each machine's health before a failover. It's a great helper, not the one making the decision. 2. What does it replace? It can't replace the judgment call of, does this piece need strong consistency or eventual consistency? Interestingly, AI systems themselves actually tip the scale toward availability. Think about it. Retrieval-augmented generation and vector databases are eventually consistent by their very nature. The index updates incrementally, with lag, so what you search is last version's knowledge. And in this setting, that's perfectly normal and totally acceptable. That's a whole different world from the penny-perfect exactness a bank's ledger demands. 3. What does it change? A new variable pops up. An agent's tolerance for stale data. Agents make decisions one after another. It reads a state from 5 seconds ago, and its next action can chain into an error. Places an order twice. The action got duplicated. So read your own writes, and the same operation giving the same result, no matter how many times you run it. These two go from old database niceties to fresh must-haves for whether an agent is reliable. Consistency, as a concern, moves from the DBA's desk over to the desk of the person building the agent.
Let me add a counterintuitive one. The way AI inference services trade consistency for throughput is different from a traditional database. That internal KV cache is soft state private to each request. Lose it, recompute it, no need for strong consistency across replicas at all. But the model's weights and the routing table must be strongly consistent. Ship the wrong version, and the output is just plain wrong. Same system, two kinds of data, two kinds of treatment.
4. What does it transform? The CAP theorem itself hasn't changed one word in over 20 years. What's changed is which data is worth paying that strong consistency price. AI has moved a whole batch of data into the eventual consistency is good enough column. So who should watch out? The engineer who takes a ledger system's strong consistency instinct and insists on wrapping a vector database in distributed transactions. You're paying top dollar for a consistency you don't even need. That's called over-engineering. 3 pitfalls, and every one of them can drag you out of bed at midnight. Number 1. Eventual consistency's last write wins will quietly swallow data.
Just like in the demo a moment ago, the write with the later timestamp won, and the losing one vanished without a sound. Put it in a real scenario. 2 people edit the same shopping cart at once. The later commit overwrites the earlier one, and the first person's changes disappear into thin air, with no error. If you really don't want to lose them, you need vector clocks or CRDTs. So concurrent writes can merge, instead of clobbering each other.
Pitfall number 2. How many 9s do I want is a budget question, not a matter of faith. 4 9s is 52 minutes of downtime a year. 5 9s is 5 minutes. Just one more 9, and the cost differs by an order of magnitude. And note this. Every extra must-pass dependency on the request path multiplies your availability downward. Chain 2 3-9 services together, and you're left with 99.8%. But 2 redundant machines in parallel, where only one has to stay alive, actually gets you 6 9s. In one line. In series, you lose 9s. In parallel, you add 9s. Your architecture diagram is really just a multiplication table for availability. Pitfall number 3. Don't turn CAP into a catchphrase. It's not, I can pick 2 of 3 anytime. It's, the instant a partition hits, pick one of consistency and availability. When the network's fine, you get to have both. I've seen way too many people use CAP as a free pass for, I'm allowed to be inconsistent. That is a complete, top-to-bottom misreading. Let's wrap it up. The one line I most want to send you home with today. Consistency is a business semantics question, not a technical article of faith. Don't open with, do I use strong consistency or eventual consistency? First ask, if this data is wrong for a moment or stale for a moment, does anybody die? Ledgers, not a single cent can be off. Strong consistency, and you swallow that latency. Like counts, a few seconds off and the sky doesn't fall. Eventual consistency, and you take back availability and speed. CAP doesn't force you to join any religion. It just lays the bill out on the table and lets you choose for yourself. Next episode, we move up one layer from the data layer, up to the traffic entry point. A single request, from the moment you hit enter to when it lands on a backend server, has to pass through DNS, CDN, load balancers, and reverse proxies. How it travels, hop by hop. Real configs, a real run, just like always. I'm Ashley. See you next time.